Hey guys, I'm Professor Turner with the Electrical and Computer Engineering Technologies program at Purdue University in New Albany, Indiana. And today you're watching a video lecture for ECET 273 Modern Energy Systems. This video today is part 3 of 4-part series in the AC Power Heads Up. This looks like it's shaping up to be a 5-part series, not a 4-part series, so consider yourself warned. In the context of electrical engineering, a load is any device in which power is being dissipated or stored in a circuit. Often the term load is more specifically used to mean a device which is connected to the output terminals of an electric circuit. So in this diagram, the electric load is represented by an ideal resistance R sub L. And that's what the L stands for, is short for load. In reality, there are many types of electrical loads. Household appliances such as microwaves and hair dryers, electronic equipment, lighting, motors. And there are even unintentional loads that can exist, such as shorts in the wiring system that consume energy. Many of these real-life loads can be modeled as an electrical circuit as a resistor, as we have in this circuit here. However, many loads exhibit properties that are not resistive and must be described in other ways. If we talk broadly about loads, we can say that electrical loads have 2 main characteristics. First is the resistance, as we're already familiar with. The second is a property called reactance. Combined, resistance and reactive effects are called the impedance of a device, often symbolized by the capital letter Z, more specifically a bold Z. And impedance tells us the relationship between an AC voltage in current and electrical devices. So if we're going to talk about how this AC voltage looks as compared to the AC current as it flows through a material device, what we're really talking about now is that device's electrical impedance. So let's look at impedance a little bit more closely. Electrical resistance is the property of a material or electronic device to resist the flow of direct current through it. That'd be this guy here, right? A resistor. The primary characteristic of a resistive circuit is the heating that's the result of the friction created by microscopic phenomena, such as the retarding forces and collisions of the charge carriers when current flows. Reactance, symbolized by these 2 devices here, is the property of a device to influence the relative timing of an alternating voltage and current, and by doing so presents a sort of impediment of its own to the flow of AC current, which is, we'll find out, dependent on the frequency of the AC waveform. In AC circuits, devices are therefore characterized by the combination of resistance and reactance, a quantity known as impedance, which is the opposition that a circuit presents to the passage of a current when a voltage is applied. So here we have a circuit. It's an AC source. We have a generalized impedance here given by the symbol Z. We are measuring the current through Z with an ammeter here and the voltage across Z with the voltmeter here. And the impedance, Z, is really the relationship to I and V. Generalized impedances in circuits can be drawn using the same symbol as a resistor. That's one technique. They can be drawn using little boxes with the Z sub S outside of the box, or they can be drawn using bigger boxes with the Z inside of the box. So we can use labeled boxes, which is the more common approach. For DC circuits, impedance simply collapses back down to resistance because there's no such thing as reactance at DC. And for AC circuits, impedance has the 2 components, resistance and reactance together. From a circuit model viewpoint, resistance represents the contribution of a resistor, clearly. Reactance, however, represents the combined contribution of 2 different circuit elements. The first is the inductor, and the second is the capacitor. So these are 2 new, what we will call passive circuit elements. 3 total circuit elements. We have resistors, a passive circuit element exhibiting the property of resistance, and then 2 reactive circuit elements. The inductor, representing the property of inductance, and the capacitor, representing the property of capacitance. So, in summary, electronic devices and materials used in electronic circuits are broadly categorized by several different properties. Resistance is the property that resists the flow of current, and reactance is the property to influence the relative timing of an AC voltage or current. Reactance is related to the internal geometry of a device and is physically unrelated to the resistance of the device. As we've seen now, reactance comes in two flavors: inductive reactance based on the property of inductance and modeled in circuits using the circuit element, the inductor, and capacitive reactance based on the property of capacitance and modeled in circuits using the circuit element of the capacitor. Finally, the term impedance, given the symbol Z, is a descriptor that takes into account both resistance and reactance. Again, in the context of electrical circuits, the term load refers to any device in which power is being dissipated or stored. From the circuit perspective, a load is defined by its impedance, comprising a resistance and a reactance. The impedance of actual electric devices may be fixed, as in the case of a simple light bulb, or it may vary. For example, if an appliance has several operating modes or settings. From a physical perspective, there are theoretically three types of loads: purely resistive loads, inductive loads, and capacitive loads. Resistive loads are those consisting basically of a heating conductor, such as nichrome wire in a toaster oven, or a filament in a light bulb. Inductive loads are the most common and include anything with a coil in it. Inductive loads require the properties associated with the magnetic fields to operate. Capacitive loads, although commonly used in electronic circuits, aren't too commonly found at the macro scale and are typically associated only with the behavior of transmission and distribution lines. Capacitive loads, as we'll see, require the properties associated with electric fields to operate. Loads also vary in the type of electric power that they can use, either AC or DC. Resistors are in different devices and can be used for either alternating or direct systems. Most motors are AC and are designed for specific voltage and frequency of operation, but some are designed to operate at DC. Many lighting requires the use of AC, particularly fluorescent lamps. Electronics are DC, but usually have an AC-DC converter included, often called a rectifier. And this table shows some examples of the different types of loads. So we've got purely resistive loads, or loads that look just like resistors from a circuit model perspective. We have incandescent lamps and heaters. Incandescent lamps are just your normal 40-watt light bulb. Motor loads are going to look like inductors, mostly like inductors. We'll find out that the actual circuit representation is a little more complex than that, but compressors, pumps, fans, household appliances, power tools, three-phase motors, all of those are going to appear kind of like as an inductor. Electronic loads, we're going to see that those represent power supplies from the computer and from cell phones, transformers, microwave ovens, fluorescence lamps, complex fluorescent light bulbs, and things like that. Let's now turn to the property of resistance and its behavior in DC circuits. Resistance is the property of a material device to resist the flow of direct current through it. In most materials, the relationship between voltage and current is a linear function. As the potential difference across the end of the conductor increases, the current through the conductor increases proportionally. Resistance, given the symbol R, is therefore a proportionality constant between voltage and current. So we would write resistance, really, of a material, the resistance of a material, is equal to the voltage applied to the material divided by the resultant current that flows through that material. So how we would indicate that is we would say that there's a current flowing through a resistor, this being the device symbol for the resistor. We've got a current flowing through it. It's DC, so it's a capital E. And then we have a voltage across the resistor, VAB. So more specifically, we would write VAB divided by I, but generally it's just kind of recognized that that voltage means the voltage across the resistor. The passive electrical component that implements electrical resistance as a circuit element is called the resistor, and it's depicted using this circuit symbol here. So this kind of wiggly line, you should have seen this in your classes. And R, the value R, denotes the resistance value of the resistor. This equation that we just wrote is where the value of a resistor in ohms is equal to the value of the voltage in volts divided by the current flowing through the resistor in amps, is known as Ohm's law, and it's named after George Simon Ohm, who was a German physicist and did a lot of work to establish the validity of this particular relationship for some materials. Most often, resistance is considered a fixed, unchanging property of a conductor that manifests in the form of heating, and this is often called joule heating, and it's typically calculated from P equals I times V. Sometimes it's P equals I squared R. So joule heating, what we mean by that is the heat lost to the resistance in a material, device, or a conductor. It's equal to the product of the current flowing through the material times the voltage drop across the material. Alternatively, using Ohm's law, we could rewrite that as is commonly written as P equals the current squared times the resistance of the material. This is really the most common formula for joule heating, especially in the power systems where we're talking about heat loss in conductors. Although it is a common assumption that resistance of a device is constant, most actual resistive devices do not have constant resistance, and the resistance will vary over time. We'll usually make the approximation in this class, and in most classes, that resistance of devices is constant for all voltages and currents, but we do want you to know that that is actually an engineering simplification. So since these variations are small enough to be negligible, and in most cases we will assume the simplifying a function about resistive devices holds, then we'll use ideal resistors in circuit analysis. So now we're going to introduce this term ideal. What does that mean? Well, we're representing the behavior as a non-changing resistance, even we know that that's not necessarily true. So therefore we call it an ideal resistor. It behaves ideally. The qualifier ideal reminds us that the resistor model makes several simplifying assumptions about the behavior of the actual devices, and primarily, like I just said, that the value does not vary over time. Resistance of a device is measured in units of ohms, where 1 ohm is equal to 1 volt per amp. Right, or the resistance between 2 points of a conductor when 1 volt is applied that produces 1 amp of a current. So an ohm, if I've got some sort of material and I apply a volt to it and I measure 1 amp, I know that that's 1 ohm of resistance. So it's a derived unit based on the volt in the amp. Very often, this relationship is rewritten for circuit analysis as VAB equals I times R, or the voltage drop across a resistor is equal to the current flow through it times its resistance. V equals IR, very famous Ohm's law, probably the most basic of the electrical engineering and engineering technology equations. You could also rewrite this just on a little bit of simple reorganization as I, or the current through the device, is equal to V over R. So why do we have these three kind of competing definitions? Well, the bottom two are really used for circuit calculations if you're trying to establish the values of voltages or currents in a circuit. And this formulation, this is actually kind of my favorite because it tells you what resistance is, right? This is Ohm's law in kind of its definition of resistance, where the other two are kind of more utilitarian reorganizations of it. So these again are done for the purpose of circuit analysis because usually the value of resistance in the circuit's already known. Using these formulas we can reference the current through the resistor to the voltage at the terminals of the resistor, and it's kind of become standard to say that current enters the positive terminal of a resistor and produces a voltage drop across the terminals of the resistor. So what we would say is that VAB, I've kind of indicated that here already, is that if a positive voltage is applied to A with respect to B, that means current is going to enter the positive terminal. Alternatively, if we had just spec'd the current flowing into the terminal A, we would have known then that VAB is positive with respect to A. So again, it's become standard to say that current enters the positive terminal of a resistor and produces a voltage drop across the terminals of the resistor. So I entering the positive terminals, the voltage drop across the terminals. Since resistance is a material property, the resistance of a device is actually dependent on the material it's made of as well as the size and shape of the device, and can be calculated as resistance equals resistivity times length divided by cross-sectional area. Symbol for resistivity is rho, length is cursive L, cross-sectional area is capital A. So in this cartoon over here, you can see L is the length of the device, cross-sectional area is going to be height times width, right? Because this is rectangular. If this was a circle, we'd have to calculate the cross-sectional area appropriately. So again, in this equation, total resistance is equal to resistivity. That's measured in ohms per meter. And it's the material property. Most often you'll find this looked up. You'll look it up in engineering tables for different materials. L is the length of the material in meters. And again, A is the cross-sectional area in meters squared. Sometimes, particularly when evaluating the resistance to current flow in wires and cables, the resistance of a material is given in an inverse form, and we call this conductance. And similarly, there is another term for resistivity called conductivity, which is its inverse. So we would say that for conductance, that's given capital G, it's defined as 1 over the resistance. And conductivity, again, is the inverse of resistivity, and its symbol is sigma, and lowercase sigma, and it's defined as 1 over rho. Conductance is measured in 2 units. The first is capital S. It stands for Siemens. That's spelled S-I-E-M-E-N-S. More commonly, it's measured in an upside down ohm symbol, and that is a mho. And then since conductivity is the inverse of resistivity, we can kind of infer what the units are going to be. It's here it was ohms per meter, and so conductivity is going to be mhos per meter. Right. Mhos per meter is the unit there. For example, an 8 ohm resistor is going to have a conductance of 0.125 mhos. It can also be said that an 8 ohm resistor has a conductance of 0.125 Siemens. It means the same thing. There's no conversion between the two. Siemens and mhos are equivalent. You'll notice again that the unit mho, it's just the word ohm spelled backwards. In the literature, mhos and Siemens are kind of used interchangeably. I think more frequently you'll see this unit mhos, maybe because people think it's funny. I'm not actually sure why it's more common. I think it's a little funny, right? Ohm backwards. All right, so let's work an example of determining the DC resistance. In this example, we've got the voltage and current that are being measured at the output of the terminals of some unknown device. So we've got some device, we don't know what's in this black box, but what we do know is that they've applied a terminal voltage to the device and then measured the terminal current. And then we've collected a table of these shown here. So we've got the terminal voltage measured in volts, and we've got the terminal current measured in amps. What we want to do is use this table of information to construct a circuit model of the device using the current and voltage data. So if we look at this table, what this table is telling us is that if we applied negative 40 volts to the terminals of the device, we measured negative 10 amps of current flow. If we applied 0 volts to the device terminals, between the device terminals, we measured 0 amps of current flow. If we applied 40 volts between the terminals, we measured 10 amps, and then the same for the other measurements. So let's solve that. So what we're going to do is we're going to just plot these numbers on a graph of voltage on the x-axis voltage on the y-axis and current on the x-axis. So we come here, we see V of t volts is negative 40, so we come down to the negative 40, and we go to the negative 10, so that's 1 point. And then V of t is negative 20, and I of t is negative 5, so that's negative 10, negative 20, negative 5. There's a point at the origin, 0, 0. We then have the point 20, or 5 comma 20 in this case, 5, 20. And then we've got the point 10 comma 4, 5, 10, 10, 20, 30, 40. So those are the plots. So there's not a lot of data here, and to really get a great idea of what this load box looks like, we would have to collect more data points. But with this, we can safely assume that the equation of the line illustrates that the terminal voltage is directly proportional because we can see that this is a straight line. So we see that the terminal voltage is directly proportional to the terminal current. If we were to write an equation for the straight line, we would just see that V of t, the terminal voltage, is equal to 4 times the current measured through the terminal. So in terms of Ohm's law, this device is behaving like a 4 ohm resistor. V of t equals 4 ohms times I of t. Right, so here we see that for an ideal resistance, the resistor is equal to the slope of the IV graph, which will always pass through the origin. So to determine this, all we did was had to determine the equation of this straight line, right?